All right, so in the last lecture, I talked about graph attention networks, and now I introduce another important class of graph neural networks, which is called graph convolutional network, GCN. And as you know, we really need these kinds of data structures, these graphs, because many problems are essentially graphs. And so we can think about graph neural network as a simple message passing algorithm. For example, in label propagation, for example, you have some semi-supervised learning. You have some labels for some nodes, not all of them, maybe 5% of them, because supervised data is expensive, and then you want to infer what are the other labels of the nodes. So this is the algorithm of label propagation, but it is only labels. So for each node we have a label. But here we want to represent each node for an embedding. So for each node is just a vector. So the same idea could be used for in this way, and it is called vector propagation because we in the context of graph neural networks we call it aggregation, and this is traditionally the first article. This is the first article that introduced graph convolutional networks for semi-supervised classification, and as you see, this is traditional deep learning. Of course, deep learning is new, but the new but modern approach is the graph approach, graph neural network. So now we respect the distribution of the data. So unlike here that we give it and we assume we have IID data, although the distribution of data is not IID. And it is concentrated in some areas more than others, so it's not fair to consider it as an IID. But in the modern approach, we are talking about graph neural networks. So everything is just in other layers we have the same nodes, but at the end we have some outputs because these outputs are the only nodes that we have some labels or some data or anything so that it could be used for supervised learning. And that's so it's almost the same. Even the convolution, everything is almost the same in parallel. So the graph convolutional neural network is, so we use weights in updating hidden states, these weights. But nodes are differently updated and respecting individual node features. And of course, weights are shared for all nodes. So when you go to the next layer, your embedding changes. So for each node in one layer, we have some embedding, but in the next layer, you have a difference, and it is updated like this. And so you can say that this W could be factorized like here. So all it's doing is just taking the mean and multiplied by weight matrix W. And we call it aggregate. So this is the aggregate, and combine it by previous embedding, you get the new embedding. But it is implemented in the next layer. So it goes to the next layer, and depending on the number of layers, you can have a more accurate, because it has been all data is aggregated. And so the neural net just learns these weights in each layer, weights of each layer. So it's a layer-wise propagation rule. And the adjacency matrix, we multiply to understand which nodes have which neighbors. And the graph convolutional network is just the stacking all of them. So as I said, it passes to the next layer. And there are three stages of graph convolutional neural network. We collect the neighbors embedding, we aggregate embedding, and pass it to a dense neural network. So it's nice to see graph convolutional networks. It's nice to compare it with graph attention that I explained in the previous lecture. And you will notice that in attention, graph attention, it's just a weighted sum of these embeddings, not just. So let's say we treat different nodes differently because, for example, this relation, it attends more to this than to other nodes. So they are almost the same. So all of them have some activation. For example, ReLU, the nonlinear activation, and all of them should be learned. Both of these paradigms have a weight matrix to be learned, and just in the graph attention, you add some attention. So the two enemies of human happiness and pain and boredom. So because if we just use reinforcement learning, we combine it by relational graph neural networks. Pick any one you want, graph attention or graph convolution or any other approach. Then you can create very new algorithms that enhances the development of reinforcement learning. And I think that in future, reinforcement learning could change the paradigms of both supervised learning and semi-supervised learning, as well as unsupervised learning. So it may be the basic infrastructure of all learning paradigms that we know.